Hey everybody. So let me just do a quick recap of the notes. And these notes I wrote before I knew how I was going to be able to communicate with you guys. So they're kind of long because I was thinking that you would have to learn every single thing from a piece of paper. But I think what I'll do in the future is make them less long and then make a little video to go with them. Okay, that can help you clarify afterwards. Okay, so we're going to look at a pretty simplistic little problem down here to give us an idea of how calculus works. And calculus basically says, there's some really hard, icky problems out there. And what you need to do is just break it down into some little small problems. And those small problems are much easier than the big problem. Get the answer to all the little small problems and add them up and ta-da, problem solved. Okay, so I made a copy of that one so I can show you a method that we could use. If we had to find the area underneath this curve from 1 to 8, well, there's nothing in any class that we've done so far that has taught us under a curve. Like if we had a semicircle, we could do that. So if there's things that we have formulas for, but just some general curve, like say the sine function. We have no formula to find the area. Okay, so calculus says, well, go ahead, break it down to something smaller. And we're actually going to do a problem, or this type of concept is going to come up in second semester. Okay, so one thing we can do is we can just put a bunch of rectangles in here. Well, we know how to find the area of a rectangle. Now, there's lots of methods, so I want you to think about how I'm going to do this. I'm going to look at the left side. Okay, so you'll see there's a thing called a right side, a midpoint. That's all for later. I'm just going to go from the left and I'm going to go straight across. And I'm going to make a rectangle. Okay, so this is only 1 wide right here. And I picked 1 on purpose because it's going to be really easy. Well, the height of this guy right here looks like it's about 2.8. So I'm going to say, okay, if the height is 2.8 and the width is 1, then this rectangle has an area of about 2.8. Okay, now at 2, I'm going to go up and go over. Okay, so notice I go straight across right there. Well, that looks like it's at 3. 3 times 1 is 3. Okay, as I go over there, that height right there looks like it's maybe about 3.8. So 3.8 times 1. Okay, I'm going to do the same thing here. Looks like it's about, oops, I'm sorry, I skipped one. That one's about 3.8. This one's about 3.2. About, I don't know. Okay, come over here. This one looks like it has an area. It's a little over 4. It's maybe about 4.1. Okay. This one here looks like it's at 4. And then this last one. So I could say that the area, I could just add all those up. And I could say, well, there is about 31. And it's surprisingly pretty accurate. I see we have some underestimates right here, but some overestimates here. And we're going to see where concavity is important. That the graph is concave down and concave up. Underestimates, overestimates. That's all coming later on. But anyway, you can see that I could break it down to some really easy stuff, add them up. And you'll see in calculus that we could get even more accurate if I knew what this function was. Because if I knew the exact equation, instead of me guessing that this is about 2.8 high, I could go, well, this height is f of 1. This height is f of 2. This height is f of 3. So you'll see that we'll be able to kind of take our old math and put it together in calculus and be able to get things that we've never been able to get before. Okay, so that's what's going on there. All right, this page talks about a limit. And I want you to think about a person walking from one side of the room to the other side. And that they have to follow a little pattern that says you can only go halfway at a time. And then you have to recalculate and go halfway again. So we have a 30-foot room. The person goes halfway, 15 feet. Then they have to recalculate. Now they can go 7.5 feet. Recalculate. And they can go 1.875 feet. Recalculate. And we could do this to infinity. We could say infinite number of times you have to do this. No end. You're going to keep doing that forever and ever and ever and ever. Well, mathematically, we would say, well, they would never be able to get to the wall. This doesn't look very good. This is the word unattainable. So there's a goal, and we could get really close to that goal. We're never going to get there. Okay, that's the limit. Or sometimes, because sometimes we can. You'll see as we go. Okay, so I want you to note that when we're talking about a limit or something getting close to something, because that's what we really like to talk about, we say it's arbitrarily close, meaning how close do you want to get? I don't care. You tell me. And maybe sometimes in our jobs will tell us how accurate and how precise we have to be. But arbitrarily means like we can't say that every problem says you have to do it this many times. Okay, so that's going to really depend on what we want to do. Don't worry about that right now. This, I do want you to know this word, infinitesimally small. So we're used to the word infinity as thinking that's a big number. We don't normally think of infinity as a small number. And sometimes we say, well, you did this process infinite number of times, and now the distance is infinitesimally small, so tiny. So infinitely small, if you will. Okay, so think about infinity going in both directions. Okay, this page we talked about in class. And this page we said, okay, if you're in Math 1 and Math 2, and you'd never seen a hole in a graph, and you'd never seen an asymptote, and you never saw a piecewise function, you wouldn't even understand what's hard about the word limit at all, because you'd be like, oh, why didn't you just say what's y when x is some number? Because that's literally what it means. When x is 3, y is 2. Okay, that's easy. That's all the limit is. So if we had nice continuous graphs that had no holes, no jumps, no gaps, no asymptotes, the limit would always just be the y value that goes with that x value. Okay? Now, as we look at it from a graph, because I want you to start thinking about this in a different way. So I could head towards 3 from the left, and I would come from the left on this graph, and I would say, oh, this graph, the y value is headed towards 2. As I come towards 3 from the right, I could do the same thing. The y is headed towards 2. Okay, so we say as x approaches 3, f of x, that just means the y value, approaches 2. And this is how we write that. Okay, so that's something I want you to know for Tuesday, that's what that notation means. Okay, so that's brand new. Now, here we get, into a class now where we have a function that's a piecewise function, and it doesn't look the same. And sometimes they ask us to find a one-sided limit, and they just ask us what's happening from the left and what's happening from the right. So as I approach 3 from the left-hand side, and it looks like that. I don't put the minus in the front because that would be like as x is approaching -3. So this is saying as you approach 3 from the left. Well, as I'm approaching 3 from the left, the function is approaching 1. The y value is approaching 1. I don't even care what's happening at that value. Like, let me see here if I have a pair of scissors. I could cut, or I could like cover up that value so you couldn't even see it, because we don't care what's happening right at 3. So imagine that I covered up. You don't know if there's a hole. Okay, I didn't make this wide enough. But don't worry about what's actually happening at 3. Just say as it's getting close to 3, this y value is headed towards 1. Okay, as I'm coming towards 3 from the right, again, I don't really care what's happening at 3. As I'm coming from the right, the y value is headed right towards 2, right? Is it at 2? 1, 2, yes. Okay, so here's how I show x is headed towards the function, the limit of the function, as x approaches 3 to the right, is 2. Now, I don't care if there's an open circle, closed circle. I don't care what's actually happening at 3. And that's why I've got down here. It's okay that there's a hole. It's still approaching 3. Okay, let's go down here. Okay, so another thing that we want to learn about is what we call a general limit. So usually, like, you would have to know that we're talking about a one-sided limit. Normally, if I ask you what the limit of something is, you have to assume that you're finding the general limit. And the general limit says that you have to have the limit from the left and the right, and they have to be equal to each other. As long as they're equal to each other, the limit exists. If they're not equal to each other, the limit does not exist. So our first example, yep, from the left and from the right, they both equal 2. The limit of this function as x approaches 3 is 2. Aha, from the left and from the right, there's something different. So we say the limit of this function as x approaches 3 does not exist. Now I want you to be really careful, and it's a bad habit, and I'll catch myself doing it. We don't want to say equals dne, and we usually write dne for does not exist. But you can't equal something that doesn't exist. Okay, so just watch out for that it's just a bad habit to put an equal sign in there. Okay, so hopefully that explains and gets you started or ready to go for Monday. Have a good weekend. Bye-bye. Or Tuesday, sorry, Tuesday.